Okay, so welcome back to the Oxford Discrete Maths and Probability Seminar. So for our second talk this afternoon, it's a great pleasure to have Sarah Peluse, who's going to talk on bounds for sets without L shapes. Thanks.
Thanks for the invitation to speak. The starting point of my talk is the multidimensional generalization of Szemerédi's theorem. Which is due to Furstenberg and Katz-Nelson. They proved this in, I think, like 1978. Right? And it states that if you let X be any finite and non-empty subset of the d-dimensional integer grid, then if S is any subset of the n by n by n by n d-dimensional integer grid, and it has no non-trivial homothetic copies of X, so translations of dilations of X. And non-trivial means that B can't be 0. Then the size of S must be little o of the size of the whole grid. Okay, so this is like the finitary version of the multidimensional Szemerédi theorem. It implies that if you have a subset of the d-dimensional grid with positive upper density, then you can find a non-trivial homothetic copy of any kind of finite configuration. And to get Szemerédi's theorem for k-term arithmetic progressions, you just take d to be 1 and x to be the integers from 0 up to k-1. To get a non-trivial homothetic copy of X is just a k-term arithmetic progression. Okay, so Furstenberg and Katz-Nelson's proof is via ergodic theory, but there are now several proofs using hypergraph regularity. And these proofs do give you kind of an explicit savings over this trivial bound of n to the d. So an explicit version of the little o term. But the savings over the trivial bound of n to the d that you get is like of inverse Ackermann type. And thus it's a kind of very difficult open problem. I think first stated kind of explicitly in general by Gowers, but in some special cases by others like Ron Graham. To prove a quantitative version of this result, but with reasonable quantitative bounds for the size of S. And so by reasonable, I mean a savings over the trivial bound of n to the d of like some function that grows at least as quickly as a finite number of iterated logs. Okay, so the problem is to prove a quantitative version of this result with reasonable bounds. Oh. Okay. And basically nothing is known towards this open problem in dimension like greater than 1. Gowers proved a general quantitative version of Szemerédi's theorem with reasonable bounds. So he proved in 1998 for length 4 progressions, in 2001 in general, and the length 3 case was done by Roth in the 50s, that if S is a subset of the first n integers, which I'll now denote with these brackets around n, and it has no non-trivial k-term arithmetic progressions, then the size of S is big O of n over log n to some power that depends on k. Okay, so Gowers gets reasonable bounds in Szemerédi's theorem. He gets a savings of just 2 iterated logs to a power. And you can use Gowers's bounds to give reasonable bounds in the multidimensional Szemerédi theorem whenever your set X is all contained in a line in Z to the D, right? Because you can just look at the intersection of your set S with like all of the cosets of this line and like apply the one-dimensional results on each of the cosets, because this will give you, like if you look at the line, you'll have a linear configuration in one dimension, and any kind of linear progression or any linear configuration, or I guess, linear configuration would be contained in some arithmetic progression of some like finite length. So then you can just apply Gowers's result. So when the set X is all contained in a line, then we have reasonable bounds. And when we let X have like some point, or not all points contained in a line. So when we have like a genuinely multidimensional configuration, reasonable bounds are known in basically exactly one case. And that is for 2-dimensional corners. Okay, so this is when you take X to be the set of pairs 0, 0, 0, 1, 1, 0. So there you're looking for copies of the configuration that looks like this. On reasonable bounds for sets lacking corners was proved by Shkredov in 2006. Okay, so we showed that if S is a subset of the 2-dimensional integer grid of side length n, and it has no non-trivial corners, then size of S is big O n squared over log n again to some power. Okay. So then by applying like a linear transformation, you can use Shkredov's result to get bounds for sets lacking any like 3-point configuration, like not all 3 points contained in a line. But this is all that's known. So there are no known bounds for any 4-point configuration that's genuinely multidimensional. Okay, so there's a few natural ways of adding like a 4th point to the corner configuration to get I guess like candidate like 4-point configurations to consider. So if you have a corner in 2 dimensions, you can add like a 3rd point in a new dimension, or sorry, a 4th point in a new dimension to get a 3-dimensional corner. Or you can add like the 4th vertex of the square. So this gives you like an axis aligned square. Right, so no bounds are known, or no reasonable bounds are known for sets lacking 3-dimensional corners or axis aligned squares. And these, seems to be like very difficult problems to do this. And the second configuration of axis-aligned squares is the topic of a conjecture of Graham. I don't actually know when he made this conjecture. But he conjectured that if S is a subset of the natural numbers across the natural numbers, and it satisfies that if you sum over all pairs in the set, n and m, the reciprocal of n squared plus m squared. So if this diverges, then S must contain an axis-aligned square. And Graham actually conjectured more generally a homothetic copy of any grid. And if you were able to prove good enough bounds for the size of a set lacking axis-aligned squares, then you would be able to prove Graham's conjecture, at least in the case of axis-aligned squares. Okay, so no bounds are known for sets lacking three-dimensional corners or axis-aligned squares. And yeah, the problem of doing this seems pretty hopeless. But the topic of my talk is a different 4-point configuration, for which I claim you can prove reasonable bounds in the multidimensional Szemerédi theorem 4. And this would be for, if you take a corner and then you add your fourth point to make a 3-term arithmetic progression vertically, and then one more leg of the corner. So it kind of looks like an L shape. And this is why I call them L shapes. And I can prove reasonable bounds right now in the finite field model setting. So we have to fix a prime P that's at least 11. Then if S is a subset of P to the n squared, and it has no non-trivial L-shaped configuration. So that means configuration of the form xy plus z, y plus 2z, x plus cy, with z not being 0. Then size of S must be big O of P to the 2n, the size of the whole product set, over some finite number of iterated logs. Okay. So I guess some remarks about this. So first, the number of iterated logs is 24 trillion. I can't promise you that it's any less than 24 trillion. And I recently learned that trillion means something different in British English than in American English, so I'll write down the number. Okay, it's this number. Okay, but it's a finite number of iterated logs, and that's what matters for the problem. And the argument I did in the finite field setting should adapt to the integer setting. At least I think the challenges of doing this are purely technical. You don't really need huge new ideas. And also, yeah, the theorem, both in the integer and finite field model setting, should generalize. to any set X with all but one point contained in a line. Okay. Yeah, but this doesn't cover the case of axis line squares or three-dimensional corners, because you need, yeah, because there you would have like 2 points off of any line. So before I start talking about the proof further, is I should ask if there are any questions about anything I've said so far. Okay, so I guess there are no questions. So I'll continue. Okay, so I'll begin, before I start talking about the proof of my result, I'll review kind of what straight up does, but in the finite field model setting. Okay, I'll first start with some notation. Okay, so I'll take G to be Fp to the n to save some writing. And then for any functions f0, f1, and f2 on G cross G that are complex valued, we define lambda sub a corner of the functions to be the trilinear average of these functions over corners. So we average over x, y, and z in G, f0 at the first point of the corner, f1 at the second point, f2 at the third point. Okay. So note that if you plug in the indicator function of a set into lambda, you just get the normalized count of corners in the set S. So this is the number of corners. Divided by size of the group squared. No, cubed. So this counts all corners, not just the non-trivial ones. And I'll also define the two-dimensional box norm. On G cross G. So the fourth power of the two-dimensional box norm is the average over x, y, x prime, y prime in G, f of x, y, of x, y prime, of x prime, y, of x prime, y prime. Okay, so it's like a weighted count of C4s. Okay, and I think this is all the notation I need to start talking about Shkridov's argument. Okay, so we'll assume that S has no non-trivial corners. And let's say sigma is the density of S in G cross G. And we'll set f sub S to be what's called the balanced function of S. So this is the indicator function of S minus its density. So that now f sub S has a mean 0. And so Shkridov's argument proceeds like via a density increment argument. Okay, and I guess if you don't know what that means, I guess you'll see what I mean when I start writing the outline. Okay, so here's the outline of the argument for corners. Okay, so the first step is that you can write using the multilinearity of lambda, the weighted count of corners in S as the sum of two terms. So we use that as linear in like the first component to get a term with arguments balanced function of S and then two indicator functions plus sigma times constant function 1 and then two indicator functions. And then you can bound this term from below using Cauchy-Schwarz and get that it's at least like sigma cubed. Okay. But if S has no non-trivial corners, then this left-hand side must be very small, right? Because it would only count the trivial corners. But then we know on the right-hand side, like this term is pretty large. It's like a constant depending on sigma. So then in order to cancel out this larger term, like this first term on the right-hand side must be pretty negative. Okay, so you can then deduce that if S has no non-trivial corners, and little n is sufficiently large in terms of sigma, then the size of this first term on the right-hand side, the one involving the balanced function, its absolute value must be large. So say larger than sigma cubed over 2. Okay. And I guess the first real step is to show that whenever F0, F1, and F2 are one bounded, lambda of F0, F1, and F2 is controlled by the two-dimensional box norm of F0. Okay. And this is just proved using Cauchy-Schwarz a couple of times. Okay, so then we can deduce from combining this with the 0th step that the two-dimensional box norm of the balanced function of S is large. So at least sigma cubed over 2. Okay, so for the second step, or second real step, we have that if F sub S has box norm at least sigma cubed over 2, then you can find a product set on which S has increased density. So there exist sets A and B in G that are pretty large. So let's say both of density at least some power of sigma, such that S has density at least the original density sigma of S on the whole space plus some absolute constant times some bounded power of sigma on the product set A cross phi. Okay, so then what you would hope to do is say, okay, so now S has increased density on this product set. Like, let's try and run the argument again, but localized to the product set, because S still, when you intersect it with the product set, it's still going to have no non-trivial corners. So then your hope would be to like iterate the argument, getting an increased density at each step, but this can't go forever because you can't have density greater than 1. So then at some point, our original largeness assumption up here on the dimension n must fail. And then you can kind of retrace your steps to get then an upper bound on the original density sigma of your set S. And yeah, so this is a density increment argument. But the problem with this is that here, like A and B are basically arbitrary, aside from being like kind of dense in G. And this proof of step 1, which I said is just Cauchy-Schwarz, it kind of like, it's very inefficient for just general sets. So when you do this Cauchy-Schwarz, you get various averages over like linear configurations that you want to then like evaluate and say are like very close to like what you'd expect them to be. And if you can do this, then this is kind of an efficient Cauchy-Schwarz argument where you don't lose any density factors when you like localize to a product set. But this kind of only works if A and B are sufficiently like Fourier pseudo-random. So iterating the argument only works if A and B are sufficiently Fourier pseudo-random. Okay, and this means that all of their non-zero Fourier coefficients are not too large. But before I say is how to fix that problem, I'll first say like very quickly, okay, what goes into this density increment step? I mean, this is basically just the statement like that if your graph has like too many C4s, you can find like a big bipartite graph like on the inside that has like increased like density, right? So this is just kind of like an averaging argument. Yeah, so the proof of this is not very hard. Okay. So to fix this issue, Shkredov introduced a pseudo-randomizing step into his argument. Okay. So you can basically using an energy increment argument, in the same way that you would prove Szemerédi's regularity lemma, partition G cross G into cells of the form the product of two cosets of the same subspace. here W is some subspace of G. So partition G cross G into sets of this form, on most of which A and B are pseudorandom in their respective factors. Okay, so this means you look at like A intersect this set and like B intersect that one. And for most of the parts of the partition, A and B are sufficiently pseudorandom in these factors. And then just by an averaging argument, you'll be able to find like one of these cells in which like A and B are both sufficiently pseudorandom and still pretty dense, and on which S still has increased density, sufficiently like greater than sigma. So then you can just restrict your attention to this product of cosets, and say like translate them to the origin, and then you can just basically assume that like A and B are both sufficiently pseudorandom, and then you can iterate the argument. So this lets you just restrict to the case in this previous part where both A and B are pseudorandom. So this is how Shkredov's argument in the finite field model setting goes. Is to review, step 0 is this trilinear form involving the balanced function of S is large if S has no non-trivial corners, and N is sufficiently large in terms of the density sigma. And then we can bound this trilinear form by some norm. So then we get that the norm, this box norm of the balanced function is large. And then from this norm being large, we got a density increment. And then we can pseudorandomize and assume that the sets in the product set on which we got the density increment are sufficiently pseudorandom that we can iterate the argument. And I guess one more thing I want to point out is that if you're kind of a bit more careful in the beginning, like 3 steps, I guess 0, 1, and 2, then you can identify the obstructions to uniformity for corners. So if S as far from the number of corners that you'd expect in a random set of the same density sigma, so far from sigma cubed, because there are 3 points in the corner, times size of G cubed corners. Then the balance function of S must correlate with either the indicator function of a product set, which is the case that we used in the argument, or one of 2 types of skew product sets. Okay, so instead of x is in A, y is in B, we have the sets x, y, so that x is in some set A, and x plus y is in some other set C, or y is in B, and x plus y is in some other set C. Okay, so the failure of a set behaving like randomly with respect to the count of corners can be explained by correlating with a product set or a skew product set. Okay, so now I'll start talking about L shapes. Okay, so here, the obstructions to uniformity are not just kind of very like or more complicated intersections of like product and skew product sets, but also very general sets of the form. Pairs x and y in G cross G, such that y is in some affine subspace that depends on x. For each little x. So for example, you could take pairs x and y such that some function phi of x dot y equals 0. And I then even take phi of x chosen uniformly at random. And then independently for each x. Okay, then you can check that this set has like far from the random number of L-shaped configurations. Okay. And these kind of new sorts of obstructions to uniformity are the main reason that the study of L-shaped configurations is like more difficult than the study of corners. Yeah, so dealing with these is like where all of the like interesting stuff happens. Okay. Okay, so maybe to tell you what that interesting stuff is, I'll similarly to the case of corners define this multilinear average over L-shaped configurations. Okay, and also define for any pair AB and G cross G, the multiplicative discrete derivative of a function. Okay, so this is f of xy times f of x plus a y plus b, the complex conjugate. Okay, so the proof of my result, it follows kind of the same general like structure of the proof of Skradov's result in the finite field model setting, but with yeah, kind of new things happening because of the existence of these things. Okay, so zeroth stuff is similar. So by the multilinearity of lambda, if S has no L shapes, then one of the averages lambda balanced function, 3 indicator functions, lambda 1 balance function, 2 indicator functions, or lambda, 2 ones, balance function, 1 indicator function. One of these 3 terms is large. And the kind of the most interesting case is when this first term is large. Okay, and then a second step, we can similarly show that if 0, F1, 2, and F3 are 1 bounded, then lambda is controlled by some norm of F0, which I guess I'll denote with a star. Okay, and this norm its 8th power is the average over x, y, h1, h2, and h3 all in the group of delta, this multiplicative discrete derivative applied with h1, 0, again with 0, h2, and then with 0, h3 to f, and then averaged over x and y. Okay, so it's probably not obvious that this is a norm, but it is. Okay, so then the second step is that you can again like deduce from this norm being large a density increment for S on some set, and the in general we get a density increment okay, also considering the less interesting cases of when this and this are large, you get a density increment on a set of the form pairs x and y, such that x is in some set A, y is in some set B, x plus y is in C, and then 2x plus y is in D. So this is like an intersection of some product sets and skew product sets. So a set of this form intersected with a set of the form phi, this union of affine subspaces that I showed you before. So the proof of this, it's basically a much more elaborate like averaging argument. And then when you kind of do the density increment and then have to run everything relative to the set T or sets of the form T, then you also need at some point in the density increment step use of the transference principle. So just, yeah, I guess just a little bit more difficult than the argument for corners. So then if you want to iterate the argument, you'll need A, B, C, and D, these sets, and phi to be sufficiently pseudo-random. For some appropriate notion of pseudo-randomness. Okay. So you want a notion of pseudo-randomness that will work for this first step, which analogously to the corner situation is just proved by a bunch of Cauchy-Schwarzes. But that is also amenable to like a kind of straight up like a pseudo-randomization argument. So it must be amenable to some sort of energy increment method. And for A, B, C, and D, it's, yeah, really not hard to see what that should be. So what we end up taking is you want like A, B, C, and D to be sufficiently pseudorandom with respect to a Gowers uniformity norm of the right degree. So I think I take A, B, C, and D to be pseudorandom with respect to like the Gowers U10 norm. But then what the right kind of notion of pseudorandomness for phi should be is not as clear. So like one natural, I guess, first thing to try, which is the first thing that I tried, is that you could take, like, let's say phi is of this form, except that little phi is not chosen uniformly at random anymore. But that phi is just pairs x and y such that y ends up in some genuine subspace of codimension 1 that depends on x. So then it would suffice for this first Cauchy-Schwarz step that phi is not an approximate polynomial of bounded degree. But this condition on big phi is not sufficient or doesn't, I guess, or isn't amenable to like an energy increment, like pseudorandomization type argument. Because there are kind of inverse theorems for approximate polynomials, but they just tell you that then you must equal a genuine polynomial on a large set. It doesn't tell you this on like a subspace or anything. So if you kind of went down this route, you would end up with tower type bounds. So then I didn't go down this route. And it turns out that an appropriate notion of pseudorandomness for phi is that its indicator function, like as a function of two variables, is pseudorandom with respect to the Gowers U8 norm on the product group G cross G. And this is also like the U10 norm for these functions living, or these sets living in G. This is amenable to an energy increment type pseudorandomization argument, but then it's not as clear that this works for this step where you have to Cauchy-Schwarz. And that this is kind of a sufficient notion of pseudorandomness for that step. Actually takes some work to prove, and you need to prove some new results. Kind of on the combinatorics of approximate polynomials. Okay, so to finish, that like once you have the right notions of pseudorandomness, you can make everything work. So then the last step would be to run a similar pseudorandomization procedure. And here I need to use the inverse theorem of Gowers and Milosevic. For Gowers norms over finite fields. And this is the source of these 24 trillion logs. So their result, so I need it for the U10 norm, and the number of iterated logs in their result grows like exponentially, or maybe even worse than exponentially in S. So that's why, that's why there's 24 trillion logs. So I need to use this result. And then also, so this will give you like correlation with polynomials. And then I need a result of Cohn and Tal. that lets you linearize these polynomials. And it basically tells you any polynomial on fp to the n, or for any such polynomial, you can find a partition of fp to the n into affine subspaces of not too small dimension on which the polynomials are constant. I guess this loses you like a couple logs, but it's nothing as bad as whatever the Gowers-Milosevic result gives you. Okay, so I think, yeah, that's all I want to say. So I'll stop here.
Great. Thank you very much, Sarah, for a lovely talk. I think that's certainly the largest explicit number we've ever had in this seminar. So I'd like to invite people to ask any questions that they have. Perhaps I can start by just asking you to tell us briefly what the obstacles are to proving this result in the integers.
So in the integers, you would do the same thing, but now subspaces are replaced by Bohr sets. And the polynomials will be replaced, or the polynomial phases will be replaced by nil sequences. And I think like dealing with nil sequences shouldn't be too annoying, but then doing everything relative to Bohr sets will be annoying. And then you'll also have to make sure, right, if you just have like two linearly independent vectors, then, and then you like, I don't know, like take the orthogonal complement of like the span of these, like, you know, like what, like how large it's going to be. But then when you're working with Bohr sets, like you're going to have like a good notion of like what are like sufficiently independent like phases, and you have to make this all quantitative. So it'll be annoying, I think, but doable.
Thank you. Does anybody else have a question? Okay, I can't see any out there. So what I'm going to do is I'm going to stop the recording, and then I'm going to invite everybody to unmute and give Sarah a big round of applause for a lovely talk.